Okay, here's a problem that's a little bit different than previous problems where there's a voltage source, the 0.6 volt source, where neither side is ground. So we're going to see in this problem how you handle a case like this. We already know, and you can see in this problem I already have our reference node, which is the ground node, circled in red here. And we already know from previous problems that if we have a voltage source where one side is ground, the other side, the node that the other side of the source is connected to, is known. So this node here has 20 volts with respect to ground, so that's a known node. And then also over here, this node, okay, that's in between this 1K ohm resistor and the plus side of this 5 volt source, well, that's also known. Okay, there's 5 volts at this node with respect to ground. So what we have here is two unknown nodes. There's an unknown node here that I'm going to label A. And on the other side of this 0.6 volt source is also an unknown node that I'll label B. Okay, you see when you have a voltage source where neither side is ground, the value of that voltage source, 0.6 volts in this case, tells you the difference in voltage between the two nodes that it's connected to. So we know that VA is 0.6 volts higher than VB. And the reason why I know it's 0.6 volts higher instead of 0.6 volts lower is the polarity. Okay, remember the polarity tells me the higher end of the voltage difference. So since node A is connected to the plus side of this 0.6 volt source, node VA is 0.6 volts higher than node VB. But we don't know what the voltage at node B with respect to ground is, or what the voltage at node A with respect to ground is yet. But we will after we write our node voltage expressions. So to set up our node voltage equations, I'm going to define a current like this. Okay, then I'm going to call I1. And I'm going to call this current I2. Okay. This current through the 0.6 volt source, I'm going to label IS. And then this current through this 1K here, I'm going to label I3. Try that again. So this here is I3. Alright, now I do my KCL equations. So KCL at node A, okay, is going to be I1 flowing in, and that's going to equal I2 plus IS, which is flowing out. Okay, and then KCL at B is just going to be IS, which is flowing in, and then I3. Alright, so first step, node voltage method, you write your KCL equations. Now I'm going to write these currents in terms of voltage using Ohm's law. So for I1, it's just going to be 20 minus VA over 1K. I2 is just VA minus 0 over 1K. Now, see, this is something we haven't seen before, and that's when you have a current defined through a voltage source like this, you can't use Ohm's law, okay, because if you were to take the ideal internal resistance of the voltage source, which is 0, this term would blow up because you'd have 0.6 volts divided by that ideal internal resistance of 0, which is infinity. So we're just going to leave that current as IS, and then you'll see what's gonna, or how we'll take care of it in the next expression, because here, okay, we have IS on this side of the equal sign for the KCL at node B, but we can write I3 in terms of voltage using Ohm's law, because I3, which is this current right here, okay, that's a 3, is the current through this 1K. So we can use Ohm's law there. So this would just be VB minus 5 over 1K. Alright, so now I can take IS, plug it into this expression here. Right, so now after I plug in my IS into my equation at node A, we would get 20 minus VA over 1K. Okay, VA let's see, VA divided by 1K, and then plug it in here for IS. This would be plus VB minus 5 over 1K. So you can see now that we have one equation in terms of voltage, but there's two unknowns, right, VA and VB. So we need another equation in order to solve, and the way we get that other equation is we go back to what I was talking about earlier, that this voltage source between these two nodes tell us the difference between the two node voltages. See, I know node A and node B differ by 0.6 volts, and the polarity tells me which one is greater. So node A is 0.6 volts greater than node B. So I can write that VA minus VB is 0.6 volts. Alright, so there's your two equations, your two unknowns. What I did is I solved for VA, and if you solve correctly for VA, VA comes out to 8.53 volts. So that means VB has to be 0.6 volts lower. So VB is 7.93 volts. Okay, so the key points in a problem like this is that when you have a voltage source where neither side is ground, just label the current through it as IS or some other variable. Realize that you can't use Ohm's law to get the current through the source in terms of voltage. You're going to have to do that with the KCL equation at a different node, where in this case it was node B. And then you're going to end up with an equation or equations where you have one extra unknown compared to the number of equations you have. So you're going to have to write another equation based on knowing that the value of the voltage source between the two nodes that aren't ground gives you the difference between those two nodes.